what is the link now between nuclear fusion power that we just spent the last 20 minutes or so on it to air sanitization in order to mitigate the spread of this coronavirus? The link lies in this topic, plasma technology. The fusion research involves the study of plasma because the field involved has to be at a very high temperature, so-called gas state, but by that time, they will all become ionized, and we call this state plasma. So let's take a look at plasma technology. So first case will bring us back to the basic question, what is a plasma? Now plasma, we call it the fourth state of matter. We'll start with solid like ice. If we give it heat, you can melt ice to become water, and that's liquid. Now, if we continue to heat water, it will turn from this liquid state to the gas. We get steam out of it. So we're now talking about gas state. Now, if you can still apply further, more energy into it, you will begin to ionize the atoms. You will begin to give sufficient energy to pull off the electrons from the atom. So on one hand, you will have negative charged electrons, and you will have some positively charged ions. Now this state is what we call the plasma state. Now plasma state could be weakly ionized, meaning you only have a small quantity of plasma, still have a lot of neutral gas, or something approaching fully ionized gases. This is 100% gas will be ionized to become plasma. While we don't talk a lot about plasma, plasma actually, if you look at the in the whole universe, actually over 99% of the matter exists in the form of plasma. One thing that perhaps we'll use them very often, but we may not think about it in terms of plasma, is the fluorescent tubes. The light tube that we use in offices, sometimes we use them at home too. The fluorescent tube actually use electrodes generating plasma, and then use the plasma to excite the working gas so that they can give off radiations, mostly in the UV, and then with the fluorescent coating on the tube, it turns it into the visible light, giving us the light that we work with. So with this, the plasma being the most abundant state for matters, and yet we don't talk about or see much of it in our everyday life, because normally we only see matter exist in solid, liquid, and gas. Only in few places, usually confined within, like a fluorescent tube, within the tube itself, we'll see the plasma state. Now, what are some of the key properties of plasma that makes it different from, let's say, normal gas? Since plasma contains ionized particles, the electrons, the ions, so plasma can conduct electricity. Normally, gas cannot. So if it can conduct electricity, then now we can channel electrical energy into the system in various fashion. We can make use of it. And we'll talk about it later in how we can use this energy. We've been talking about the electrons and the ions. These two species represent two energy channels. Each have a very different characteristics. Electrons is very, very light. So even if electron carries significant amount of energy, we normally won't feel heat from it. When we talk about heat or temperature, we normally refer to energy of the more massive ions. So the ion would be the one that will give us the temperature feeling. And if we need to do some sort of surface notifications. Iron will be more effective because it has much more mass. It has a stronger momentum. You can do more, let's say, sputtering, that kind of erosion kind of exercise. So there are two energy channels that we can use. To define a plasma, there are two key parameters. Of course, the temperature related to it, and also the density. Now, if you look at the diagram now on the left-hand side, the y-axis refers to the temperature, and you have the density on the x-axis. So there is a number of different kind of situation that you see plasma or where plasma exists. And you can see right in the middle, very low density, the middle density 10 to the 15, reasonably low temperature in this scale is a normal flame fire. Actually, at the very tip, very hot temperature tip, that temperature may be enough to ionize some of the gas, but it will be very, very low density. And if you move up a bit, that is the area that kind of plasma, that kind of temperature range, that kind of density range is what we'll use in many of the industrial applications these days. Now, if you look at the diagram, move further up in terms of temperature, you've got the solar corona, that's the outer surface on the surface of the sun. And if you move up further, you'll see a couple of things representing the magnetic confinement fusion. That is where the temperature and the density will be working. For inertial confinement, usually it will work on higher density. So it's moving more onto the right. And right at the dot, there's a solar core is at the center of the sun. That's the kind of the temperature and density we're talking about. Now go back and look at so far where we have made use of plasma in everyday life in the industrial applications. These days, we have something like we call the plasma arc welding. Because it's high temperature, you can melt quite effectively. So you can do cutting with it, or you can join things with it. And you can also use the high temperature plasma to do gasifications, or we call incineration too. And these days, we have a new generation of this incinerator to burn the solid waste. But the conventional ones cannot reach a very high temperature. So one of the problems with the conventional waste incinerators is that there could be toxic gas released from it, those dioxins. Now with plasma being operating at much higher temperature, and then the temperature would be high enough to break down these harmful gases. So there will be no dioxin released from a plasma waste burning incinerator. And then you can use plasma to do etching. Etching has been used for a long time. All our computer relies on these the electronic parts, those ICs, and they internally, they're very tiny elements. In order to cut them up into kind of different tracks and so on, we need something very fine scale etching, and this has to, then we can use plasma to do it. We have light, like fluorescent tube, UV tube for, not just for lighting, our UV tube will be for disinfection. And you know, some of you may have seen it or actually use it, the plasma display panel, the flat panel TV screen. And in those, you have tiny cell. Then when you ionize the cell and use it to ignite light, basically like a miniature fluorescent tube, very tiny dot. You have many pixels of them to lit up and to form the pattern you see. And that's how a plasma display panel works. And now we have extended plasma into the application for sterilization and air sanitization. So how can we create plasma for industrial applications? There are many different means. Basically, as long as you can inject energy into some gas, you can heat it very high temperature, or you can use microwave, laser, and also use a very simple method. It's just simply by applying two high voltages onto two electrodes. Now, with sufficient voltage, or more precisely, with sufficiently strong electric field, you can produce basically an arc between these electrodes. Now, what happens is when you have a high voltage on a pair of electrodes, let's say in air, usually you have some free electron somewhere around. We always have some ions, some ions in the air. It could be from some of the cosmic radiations that actually help ionize some of them. So you have free electrons, free ions in the normal air. So the electric field imposed by this pair of electrodes will begin to accelerate these electrons. So, or you can assist this initial ionization by some filament heated up like in a fluorescent tube. So the electron that got accelerated in the electrode would be flowing. The electron, of course, refer to the positive end of the electrode, and for the positive charged ion, it will flow to the negative. Along the way, it will pick up energy from the electric field, and it will induce further ionizations. Now, if the energy that picks up by this electron is sufficient to overcome the losses during the collisions as it's accelerated towards the positive end of the electrode, then it will have enough energy to continue the reaction, to travel further, to pick up more energy from the electric field and induce for more electron. In that case, we'll have an arc develop, an arcing. And the condition for having this so-called breakdown is governed by what we know as the Paschen law. So it depends on the pressure and the gap, the distance between the two electrodes. So there are two processes in here in order to form a discharge, either in form of a small filament or a major arc. We first have to rely on some ionization, initial ionizations. It could be close to the electrode where the electric field is highest. And then there will be a second phase. They will need to be able to pick up sufficient energy along the way as it's accelerated to the electrodes and pick up enough energy to compensate the loss along its way. Now, this is one difference between a plasma device and something we call air ionizers. There are some devices called ionizers. They can release charged particles into the air. Now, this is also useful for removing contaminants in air, because the charged particle with its electrostatic charge on it, if it gets attached to, let's say, a dust particle, the dust particle with a static electrical discharge on it, static charge on it, would facilitate it to cling on to nearby surfaces. So this charged contaminant will then be removed from air. It will attach to the surface on the wall, maybe on the tabletop. So that ionizer has a capability of helping to remove or transfer the contaminants in air to nearby surfaces. But they normally do not have very high energy. Whereas in an actual plasma, when you have this filament developed, or sometimes when it's strong enough, we call them arc. Then the energy could be very high. And in the plasma arc welding like that, the energy is high enough that it can melt many of the solid materials. Now the plasma with its energy as well as the ionized electron, you can induce a number of reactions along the way within the space between the two electrodes. Of course, you have this ionization, but you can disassociate gas in the space, like water. You can disassociate into O and OH. Now, with OH, this reticule actually can be used also to oxidize pathogens, the microbes in air. So that's one way you can achieve some level of sanitization. So when we look at the different applications like plasma processing, then it depends on what we want to achieve. We can rely on or make use of the direct actions from electrons or the positively charged ions. And also we can make use of the indirect actions from the electron through various means like excitation, reticle. UV generation is one of those that we use when the electron recombine and release energy photons, and that's how we get light or UV out of it. Now let's take a look at how UV is generated and applied for sanitization. Now, if you look at the construction of a UV tube, normally you see they will have some sort of filament, and that's the electrode right on top of it. You heat it up, so it allows to generate electron. Electron will stream out from there, inducing further ionizations. And as the electron is accelerated and have enough energy to cause ionization, at the same time, some of them will recombine with the working gas inside. Things like mercury, sometimes the tube use mercury inside. These days, they may turn to different elements. The mercury actually is not a very nice element, so it can cause pollution. So many of you, some of the fluorescent tube these days will use a different element for that purpose. So when electron actually recombine the ionized mercury, it will emit UV, and that's how it comes out. And so basically, it makes use of energy in the electron channel, and it will emit UV in a wide spectrum, depending on, actually is a number 9, depending on which kind of energy band it fall back into. Now, if you now turn to the left-hand side, the top left-hand, look at the, in terms of germicidal effectiveness, and then we normally group UV light into 3 bands, the so-called UVA, UVB, and UVC. For disinfection purposes, UVC band is more appropriate. We are talking about something below something like a 300 nanometer, that kind of thing, between 200 to 300 band. And so depending on the working gas, the main emission would be like a line emission. And so for the low pressure UV lamp, this is sitting somewhere around 250 plus nanometer. That's already a very intense study over the years on the efficiency of UV light disinfections. And the overall disinfection efficiency, or they call it efficacy, how much basically is microbe or germs that you can kill, eliminate with UV. It depends on the so-called UV dose, which is basically the UV intensity emitted times the time, how long you irradiate on it. Of course, it depends on the species. The reason why it depends on that is that some microbe will have a much harder protective shell on it, have a much stronger skin, put it that way. So you need more dosage in order to deactivate them. And you can look at, if you look at the number, the range would lie between 2,000 to 200,000. This unit called micro-1 second per centimeter square. And what it amounts to, if you use a typical UV tube, you can buy commercially out in the market. And in order to provide a sufficient disinfection, you do need to irradiate, talking about things like a few tens of minutes to a few hours. So the guideline for using UV to disinfect surgical instruments is 2 hours in the hospital. They'll put the surgical instrument in a UV chamber, turn on the UV light and have it radiate for at least 2 hours before they use the surgical instruments for operation. There are also some recommendations you see here for the dosage. If you want to disinfect water, there's some guideline from this is a US guideline about 20,000 for example. In Rome, if you want to use UV light to disinfect the air passing through, let's say, a chamber, that you put this UV tube in it. So a standard UV tube will have an intensity, the usage put out the spec, something like 100 microwatt per second, as we'll see per centimeter square at some distance. Nominally it's 1 meter. But if you place closer to it, the intensity will be higher. It has 1/d kind of dependence. The further you are away from the UV tube, the lamp, the intensity will be lower. But on the other hand, if you're actually getting closer to it, the intensity is higher. Now, let's say if this application is in the air duct. In a ventilation system, usually you will have air duct where air from a room will be sucked into the fan coil for cooling and then pass through this duct. Now, if you put UV tube in this duct, typically with a cross-section like 40 centimeter by 40 centimeter, and you have an airspeed in many ventilation systems, we're talking about 2 to 5 meters per second, that's on the level. Let's say we pick 2.4 for this calculation. And if you look at the length of the tube, so you can work out something we call residence time. This is the time the contaminant will be under the radiation of the UV, the UV lamp. So as it passes through it will be get radiated for that amount of time. So for that given length and the speed those particles traveling, we're talking about something like 0.19 of a second. So if you really want to achieve the recommended dosage, you will need something like 100 tubes in it in order to achieve the level of disinfection that you would need. Now let's now look at another applications of plasma for this time for surface sanitizations. So if you create plasma, this very high temperature gas, put it that way, is ionized gas. When you apply it to a surface, then obviously with that kind of energy, you can kill the germs on the surface. So this is a simple approach using what we call a plasma gun. This is a design where you have one electrode hidden inside and then bounded by an outer electrode. And you have you create kind of ionization at that point, then you accelerate the plasma, shoot the plasma onto a surface. And there are two approaches actually, depending on your target material. If it's kind of conducting, then you can actually attach the anode to it. So you can attract the plasma flow over easier, making it more efficient. On the other hand, if for a general purpose, you can't really attach an electrode onto the surface or make it become one of the electrodes. You really just, all you can do is to force the plasma to flow onto the surface. And this is the so-called non-transfer art. And you create the plasma, just shoot it over and spray it onto the surface. There's also another approach. This is also for a surface disinfection. Actually, this is a commercially available product. Here, if you look at the picture in there, basically is a chamber. You kind of use a pump to extract the air out. But when you first put the instrument, like a surgical instrument, you want to disinfect inside. You pump out the gas, make it kind of semi-vacuum. And that way you can create plasma easier. And actually in a vacuum state, you can control the plasma easier. And so you can ignite the plasma and then use the plasma to disinfect to clean the surface of those medical equipments. You can imagine one way to think about this is, you can imagine it's just like putting your medical equipment inside a fluorescent tube. So you use the plasma there to kill it. Now to make it work actually even better, they put in a working gas, this hydrogen peroxide. And because once you disassociate hydrogen peroxide, it will become quite oxidizing by itself, not the plasma energies to kill the germ. Just because the hydrogen peroxide itself is oxidizing, it can also kill germs by itself. So you can add this extra bonus to it if you operate in this kind of configuration. Normally in this device, you work on the semi-vacuum. We're talking about 1 millimeter mercury. There's a unit we measure in terms of the pressure inside. And then you use some radio frequency signal, kind of excite the plasma inside. And this is how it works for surface disinfection. And next, we're going to look at how we can apply for gas now. Now, here on the left-hand side, the top row, you have two parallel electrodes, one upper, one lower. So in between, you can create plasma. Then you allow using a fan to force the air to go through these two electrodes. And since there are plasma created in this space, they have high enough energy, they can actually break down the contaminants within the air passing through it. And simply that's how it works. And since we're talking about electrical energy and the mechanism basically is a physical means. So most kind of these germs, microbes, fungi, bacteria, or virus, they can all be eliminated using this plasma energy. So to create the plasma, all we have to do is to apply some high voltage onto it. And that, in fact, what will happen is you create some sort of micro lightnings. It's actually resemble the lightning we've seen in the nature, but those are huge. Here, there are certain mechanisms within the design that we restrain it to be a very, very tiny arc or filament. So there are thousands of these micro lightning, small filament, generating high energy plasma. So this is what is shown on the right-hand side. Some of the purple light, they are basically the light emitted by the plasma. So you can kind of visualize it that way. Of course, in actual experiment, if you need to detect the element, there are different ways that we can do it. We can actually observe the light emitted and then estimating how much plasma is actually in there. Or there are sometimes we can put in some sort we call probe. This is just an electrical wire. and we can then infer from there the presence of plasma. Now, since the plasma is created, first of all, by this electric field, and actually it has to be sustained by the electric field too. Yes, I just see the questions. That probably is referred to back here. I forgot, I didn't see it. What W is what? Yeah, yes, it is. In the tube, if you talk about the tube here, this is not a closed tube, it's open end. Air can actually flow, enter from one end, and then come out from the other end. So the plasma with its high energy, they can only exist in this area within this tube when there are a high electric field. When they come out from the tube together with some of the neutral air, the plasma will quickly recombine back to air. They need this continuous ionization, continuous acceleration, depicted earlier when we talk about this filament formation. So for this kind of plasma devices, there will be no charged ions coming out from the device. So in our R&D, we've kind of looked at the overall disinfection efficacy of this process, and the result indicated that we can actually achieve a very high level of removal efficacy in a very short time. We're talking about over 99% in less than 0.1 of a second. I'm going to go through this again because there's a need to distinguish what we mean by plasma technology and what we mean by ionization technology. The two technology looks very similar. They both make use of some high voltage, create ionization. In some essence, the ionizer stops at that point. But for the continuous generation of plasma at high energy, we need to continue beyond the first stage of ionization. We need to have an electric field region where we can continue to accelerate the plasma, mainly the electrons, and so that it can generate these tiny filaments, this alkane, to sustain the plasma at high energy level. So if we go back, if the number, most of the time for ionizers, the ions are actually at the room temperature. Room temperature is something like 0.025 electron volt. Now, electron volt is a common unit we use when we study plasma. It means electron volt, basically electron charge times the voltage, just the amount of energy in it. Kind of tiny, but when we refer to single particle, that is not a too tiny unit. For the plasma we're talking about for air disinfection, the plasma is in the energy range about 10 to 20 eV. Now let's now go into a bit of the details in terms of differences. To start with, when we're talking about plasma, we're really talking about energetic charged particle, not just very low energy ion floating around. And then in the plasma sanitization process, there are a number of processes: direct ionization, dissociation due to the electron energy, or can be secondary process through the electron excitation like UV and the reticle formations. Now, on the right-hand side, there's a table talking about various energy levels. Now, if you look at the so-called molecular bond, now for, let's say, organic matters, it's a long chain of molecules. So each molecule is kind of linked, tie up to the other one. And if you have sufficient energy, you can break that bond. Now, in order to break that bond, you need to apply energy. And this is what we refer to the bonding energy or dissociation energy. Now, for organic matters, we're talking about something like 0.1 to at most a few eV. And we're talking about plasma in this kind of formation using electrodes and normal atmospheric gas plasma. This is about 10 to 20 eV. Now, if you use UVC for disinfection at 254 nanometer wavelength, this corresponds to an energy level of 4.9 EV. Now, if you look at those ionizer, the air ion they generate, they are at 0.025 EV, so very small. So that's a basic principle. If your working species, your working device, generating an energy level that is not sufficiently high enough, it will be difficult to break those bonds and hence provide you with this kind of a disinfection capability. So you can see that unless you can reach a few EV energy level, the efficiency will be very low or cannot actually achieve any disinfection at all. So one way to look at it is that you can say that when we talk about plasma disinfection, it needs to be very direct because you need the strong electric field to maintain them. You can't rely on having this kind of charged particles moving away from the electric field out into the living environment. Whereas for kind of ionic technologies, they make use of this ion. But mostly, their capability relies on that electrical static electricity effect. So when the contaminants has some charge on it, they will be able to kind of stick to the surface. Now, at this point, maybe I should give some sort of warning for people interested to look at some of those devices. Now, out there in the market, there are this pendant type of so-called air purifier. You hang it with a chain on your neck. They rely on this ionizing means. They are one of the kind of ionizer. Now, since they generate static electricity and transfer it to the pollutant, let's say those germs. Now, once the germs have some electric charge on it, it would be quickly attached to nearby surfaces. It would be either to your clothes or it can be actually to your face. Those are the nearest to the pendant you're wearing. So rather than eliminating or reducing the risk of this kind of germ reaching you, you're actually enhancing the probability. And it is actually giving you a negative effect.